The next technique that we're going to learn is trigonometric substitution. So this is a technique where we're actually substituting in some trigonometric functions, which seems like it's counterintuitive in some way because you think like, okay, trig functions make things harder. But we just learned a whole bunch of different ways to evaluate integrals that have trigonometric stuff in them. So if we can take something like this, and maybe we can notice, look, this 9 minus x squared, square root of 9 minus x squared, that looks like some right triangle thing. It is, in fact, some right triangle thing. So what you can do is maybe you can, because you can't really do this integral the way it is, right? The reason you can't is it almost looks like it would be a u substitution. Hey, if instead of being x squared on the top, it was just x like that, now I made my life a lot easier, right? Because now it's just a simple u substitution. But if it's a squared in the top, it is not going to be a simple u substitution. That's why people thought, okay, what else are we going to do? And it turns out that if you try to do stuff like integration by parts, it just makes a big old mess. But if you can use this interesting sort of right triangle-y looking thing, it'll give you a substitution that works out. So let's look at this and see what this tells us when I say, oh, it looks like a right triangle-y thing. Okay? So the idea is, here's my right triangle, and this is all based on Pythagorean Theorem, right? So a squared plus b squared equals c squared, right? But c squared is going to be the hypotenuse and a and b are the legs. Now if I solve for this, if I solve for one of these guys, I'm going to get this, like if I solve for c, I'm going to get the square root of these two. If I solve for b, I'm going to get the square root of c squared minus something, etc., etc., etc. So the square root that we have appearing in our integral here, if you look at it, it's the square root of 9 minus x squared. So when I think about how did this come from the Pythagorean theorem, well, it looks like the 9 must be my hypotenuse, right? How do I think about that? Well, let's see. It's going to be here, right? And then it doesn't matter which leg I call x. Let's call it this one. And then this other leg, we'll give it a name for the moment. We can call it b, right? If I were to solve for this b, right, b squared is going to be, now I'm going to put in the numbers, right? So b squared is 9 minus x squared, or b is this square root right here. So actually this leg of this triangle is the square root of 9 minus x squared. Okay, so that's where this starts out from. I'm looking at that form, that square root, and thinking, where would that square root come on? What kind of triangle will give me that kind of square root? If I'm taking something away from 9, then 3 must be the hypotenuse. All right? So you kind of see that this is going on here. And now, if you see, all right, what am I going to do with it? What I need to do, the idea of this substitution, is to get rid of the x and to put it into theta. Right? So let's see. What do I know about x and theta? Well, sine theta, right? Sine theta is opposite over hypotenuse. It's x over 3. Wait, well, this for a second. So x is 3 sine theta. And now I can substitute this in for x and stuff, but I can also substitute it for my dx. dx is 3 cosine theta. Now what about this square root business? I can figure out what the square root is. I can do it in 2 ways. I can just substitute that in, right? So that's a little bit of work, but that's what your book likes to do. So if I want to do that work, I can substitute that guy in. 9 minus sine squared theta, right, is this. And then I have to figure out how to deal with that. This is a pain. Anyhow, what I would prefer to do, right? By the way, I left my 3, that's why. Let me do it that way. So let me do it right now, because now I have to do it the whole way to tell you that it really does work. Okay, so what you have here is going to be the square root of 9 minus 9 sine squared theta. That's going to be 3 times the square root of 1 minus sine squared theta. Well, that's just cosine squared, right? So this is 3 times the square root of cosine squared theta. So this is 3 cosine theta. All right, that worked out. It's kind of a lot of work, though, because I can also just go look at this triangle. Look at this triangle, I can say that cosine of theta is the adjacent over the hypotenuse. And the adjacent is this root. So then my square root is 3 cosine theta. So I can go 2 ways. I can use my thing here, my substitute it directly into everything and then do that. Or I can read what these things are off the triangle. So regardless, now I know what everything is, right? I have that, and I figured this out, whatever way I figured it out. Now I can put all this stuff back into here, and let's see what I get. You know what I forgot here? That's what, I forgot my d theta. So you always have to have a d theta, right, when you take a dx. And I forgot to write it there, but I remembered, so there it is. So let's see what we got here. This is going to be 3 sine theta quantity squared. The dx is all this stuff. And then I'm dividing by my square root, and my square root is this here. So that's good, because these guys cancel, these guys cancel. I end up with an integral of 9 sine squared theta. Right? And just last week, of course, we learned how to do that. We do this with the half angle formula. It's a pretty straightforward one, right? I got 1/2, and I have 1 minus cosine 2 theta, d theta. So now I'm going to erase this guy a little bit. But I want to make sure I leave that because I have to have, in the end, I have to put it into s. So then I integrate this, I get theta over 2 minus 1/4 sine of 2 theta. I should probably not have chosen this example as the very first one. Okay, we'll just go with it. Okay, so here's my answer almost, right? But I need my answer to be in x, and my answer is in theta. So I have to go back to my guys here and figure out how to put this into x. So the first one, again, okay, we have theta, we don't have sine theta. I know that sine theta is x over 3, so I can notice that if I do inverse sine on both sides, I'll get theta equals inverse sine of x over 3 here. Okay, so I'm going to need some space. I'm going to pull this down here. So this is going to be 1/2 inverse sine of x over 3. But now this second point, I've got a little bit of a problem, because if you remember from doing this stuff with trigonometry, you know, with the triangle and then with the 2 theta, like if I want sine of 2 theta, it's not 2 times sine of theta, right? I have to use some kind of identity. So in this case, the identity I need to use the 2 sine theta cosine theta, right? So this is 2 sine theta cosine theta, because sine theta and cosine theta I can read directly off my triangle and what x was. So sine theta, so let me get my 2 here. Sine theta was, where was it? Here. Sine theta was x over 3. And because I didn't erase them all, they're all on the boards here somewhere. Cosine theta was square root here. Remember, both of those we got from the triangle. Okay? I can clean that up a little bit so that my answer is sort of a little bit nicer. I get x times square root of 9 minus x squared over what, 12? But yes, so essentially that's the answer there. So there we go. I'm going to do a couple more.